Hello everyone, I welcome you all to my channel, and as many of you know, I am Gayan Fernando, and this channel is an educational channel. So if you wish to watch more videos, please consider subscribing. And I hope many of you watched the sixth part of the previous part of the series, and in that video we talked about electric cells. So the seventh part is somewhat related to that part, as we are going to talk about electric energy in this part. So let's start the seventh part of current electricity. Okay, as I said before, this part we are going to talk about mostly electric energy. So this is the content of this video. Firstly, we are going to talk about electric power, then electric energy, then we are going to talk about the relationship between the load resistor and the electric cell's internal resistor when the electric power dissipation across the external load at its maximum, and finally we are going to talk about the efficiency of electric load. So let's start with electric power. When a current is passing through a resistor, the electric energy is converted into many other forms of energy. Most of the time, the electric energy is converted into heat, as when a current passes through a resistor, the resistor is heated. And of course, sometimes if the resistor is a bulb, the electric energy is converted into light energy, and sometimes the electric energy may converted into sound, and sometimes the electric energy may converted into mechanical energy such as kinetic energy and potential energy. So the rate of the electric energy dissipation can be found using the equation P equals VI. In this equation, P is the power which is measured in watts, and V is the potential difference across the resistor or the electric device you consider, and that is measured in volts, and I is the current passing through that resistor, that is measured in amperes. So we've learned the Ohm's law before. So if we substitute V equals IR to this equation, we can obtain two more equations. P equals V squared by R and I squared into R. In these equations, R is the electric resistance which is measured in ohms. And this is the equation for to find the electric power across a resistor. If we need to find the the total electric power dissipation from the whole electric circuit, we can substitute E into V, so that we can obtain the equation P equals EI. P equals EI is used when we need to find the electric power dissipation, the total electric power dissipation from the whole circuit. E is the electromotive force of the electric cell. And next we are moving into electric energy. As we know, energy is power times time. If we multiply power into time, we can obtain energy. So we learned three equations for power before. So if we multiply them by time, we can obtain the electric energies. So electric energy can be found. VI is the power and time, so that we can obtain electric energy, and V squared by R is the power. So to get electric energy, we have to multiply by time, and I squared R is again power, and if we multiply by time, it is electric energy. And since we are talking about electric energy, there are two main units which we use to measure electric energy other than joules. They are kilowatts hour and also electron volts. 1 kilowatt hour is equal to 1 kilo is 10 to the power 3, watt is Js minus 1, and hour is 3600 seconds. So if we simplify this, we can obtain 3.6 10 to the power 6 joules. So 1 kilowatt hour is equals 3.6 10 to the power 6 joules. And 1 electron volt, 1 electron is the charge of an electron. It is 1.6 10 to the power minus 19 coulombs. That is the electron charge of an electron. Volt is joules per coulomb. So if we simplify the units, we can obtain 1.6 10 to the power minus 19 joules. So 1 electron volt is 1.6 10 to the power minus 19 joules. So it is a very small unit, and 1 electron volt is 3.6 10 to the power 6 joules. That is a very large unit. And next we are moving into find the relationship between the external resistor and the internal resistor of the electric cell when the electric dissipation, power dissipation of the load at its maximum. So this is the load, its resistor is capital R, and this is the cell, electromotive force is E, and internal resistor is simple R. So this is the current used by the electric cell is I. If we use the Kirchhoff law, E equals I times R plus R, so that we can get the current is E by R plus R. So the power dissipation from this resistor is P equals I squared R, as we talked before, and I squared is E squared by R squared from this equation, and R. So this is the equation to find the power dissipation from the load resistor. So if we need to draw a graph, the equation is E squared R plus R squared times R. If I'm going to draw a graph, between selecting the independent variable as the load resistor and the dependent variable as the power, we can see if we substitute 0 to this R, the power will be 0. So this is the point, R0, P0. And if we substitute infinity into R, we obtain infinity divided by, the denominator will be infinity squared. So the denominator reach infinity faster than the above part. So the value will be 0. And if we differentiate this equation with respect to R, dp over dr, and if we substitute 0 to that, we can obtain the power value for capital R when the power is at its maximum. So that will be simple R. So the graph will look like this. So the power is maximized when the load resistor is equal to cell's internal resistor. And if we substitute that value to this equation, we can obtain P max is equal to E squared R by 2R squared. That will be E squared by 4R. So that's the value here, E squared by 4R. So the important point is when the load's power dissipation at its maximum, its resistance will be equal to this electric cell's internal resistance. Next, we are moving into find the electric efficiency of load's resistor, external load resistance. So the efficiency is defined as the output divided by input. So the output here is the I squared R, as we talked before, and the input is the electric dissipation throughout the whole circuit, and I said that it's equals to EI. So one I is cancelled out and we obtain IR by E. And as I said previous, I showed this using the Kirchhoff's law. I is equals to E divided by R plus R. So if we substitute this to this I, we can obtain beta is equals to ER plus R. This is I times R by E. So that beta will be R by R plus simple R. So this equation can be used to find the efficiency of the external resistor, that is the resistance of external resistor divided by that value plus the electric cell's internal resistance. And as I shown before, when at P max, R equals simple R. So if we substitute this to this equation, we can see that beta is equals to simple R by simple R plus simple R, that is half, and that is half, and most of the time we express efficiency as a percentage, so that the half into 100, that is 50%. So that the electric efficiency of the external resistance will be 50% when the electric power dissipation at its from the load resistor is at its maximum. So with this part, this seventh part of the series comes to an end. So I hope you enjoyed the video. If you enjoyed the video, please hit the like button, and if you have any questions or compliments or criticisms, whatever, you can comment down below, and of course please share the video so others can watch more. And I hope to catch you guys in the 8th part. So until then, have a nice day.